Good morning, mathematicians. Actually, yesterday we were right on the cusp of having the solution to the problem. If I had literally done one more calculation, it would have been obvious. So we will amend that today. Uh, so let's do that. Wow, Ken, first in chat. Good morning, Ken. How are you today? Good morning, Raymond. Oh, you know what could be a fun series for this channel? I could go through and try and solve. I still have like. Good morning, Castica Troy. I still have a bunch of, homework assignments from. Oh, look at that! Still, look at that pause screen. Amazing. From my undergrad and stuff. Um, had to, Ken? Had to? You mean get to, right? But it'd be fun to go back and try and do my old homework assignments without studying. Good morning, Russ. Is there a universe of sets that makes mathematical statements true? Hmm? What do you mean? What do you mean by that? I think the short answer is no. Um, I'm not sure what you mean by that. Can mathematical statements be true? Yeah. Depends how you define true, I guess. uh, hello, Baobab tree. Baobab tree. Baobab tree. That's what it is. Oh, all mathematical statements are false? Okay, well, that's too bad. Yeah, so let me just remind you what were we talking about yesterday? We were trying to prove that all groups of order um, p times q squared is are solvable. And basically the thing is, if you can force the existence of a normal subgroup, then it's solvable. So that means the number of p Sylow subgroups, if it's one, we're done. Or sorry, q, let's say q Sylow subgroups. And then the other possibility is, well, suppose that there's p q Sylow subgroups, and we want to ask, well, how many p Sylow subgroups could there be? Could there be one? Well, again, if it's one, we can just apply a similar argument, normal subgroups, and we're done. There could technically be q, you would think, but remember, this has to be congruent to 1 mod q, and that would force p to be bigger than q. And so if np were q, that would have to be congruent to 1 mod p, but then that would force p to be bigger than q, which is impossible. So the only the final case that we need to consider is when we have q squared p Sylow subgroups. You're allegedly doing a reading course on differential forms. Allegedly? But haven't done anything the whole semester. Okay. Yeah. Yeah. Yeah, I'm a little worried about the state of my thesis by the deadline on Monday night. And so I'm starting to break my rule about, I'm like, I will go to bed when I need to go to bed. Electronics off at a certain time. Nothing will get in the way. And I'm like, okay, maybe this week I start to let things get in the way. Okay, so now here's where we get the contradiction. So if we have so if we were in this case, so nq is p, np is q squared. I'm going to argue we can't have both of these simultaneously. Why not? Because if nq was p, then that means that we have maybe I should do this in different colors. So from this, we know that we would have p minus 1 times q squared elements of orders 1, q, and q squared, or q squared, right? Oh wait, no, q or q squared, because I've taken out the identity with all of these p minus 1s. Yeah. Right. So meanwhile, from np being q squared, this would mean that we have q squared minus 1 times p elements of order p. And so that means that we would have p times q squared minus q squared minus 1 times p, which would be p elements of order q1, q, or q squared, right? But now here's our contradiction, right? Because it would have to then be that p minus 1 times q squared plus 1 is equal to p. Wait, why is that impossible? What did I do? I did something slightly wrong here. Oh, because p is larger. No, that's fine. Oh, yes, of course. Of course. That's impossible because this would imply that q squared is equal to 1. Contradiction. There we go. Yay, I solved it. I wonder, should I go back and I should change the name of stream. Good morning, Arad. Let me change the name of stream. Super Chad Grad solves Sylow. Yeah, that's a better name. Anywho, what's an Adele? Glad you asked. You think your favorite group theory problem is showing there are no simple groups of order 120? Maybe we'll do that one next. Why is it your favorite? If you can say that without spoiling the proof, because I assume maybe there's something slick and sneaky you do in the proof. Adele is a singer, but in fact there's more than one Adele. I think the singer everyone knows is just the Adeles of the rational numbers. But in fact, there's an Adele for every number field. So let's start with the rational numbers. Okay, my favorite theorem in mathematics tells us if you put an absolute value on the rational numbers, then up to topological equivalence, there's only the only ones are, well, there's the trivial absolute value, there's the normal Euclidean absolute value, which we put an infinity underneath, and then there's the p-adic absolute value for every prime p. And then that's it. That's all there is. And so since you get the real numbers, the real numbers are the Cauchy sequence completion of the rational numbers with respect to the ordinary Euclidean absolute value, then you might also want to create the Cauchy sequence completion with respect to the p-adic absolute values, and that's the definition of the p-adic fields. And these are all examples of local fields. What does that mean? In particular, it means Well, they're locally compact, and it means that there's a good notion we can do calculus, maybe not calculus, but we can do integration and Fourier theory on these fields. So that's cool. But this is a big infinite. Infinite list of fields. Super chat economy. Okay. Okay. What's the topology on QP? It's the topology induced by the norm. So basically, because if you take the Cauchy sequence completion, then you can extend the absolute value to your sequences, right? So if you have if you have a sequence of rational numbers, then the p-adic. So you first define the p-adic absolute value on the first you define the p-adic absolute value on the rationals. You create the Cauchy sequence completion, and then you define the p-adic absolute value to be the limit of the p-adic absolute value of the individual terms. And then you can prove that this still defines a norm, and so then therefore you have a metric. Now here by x and y I mean sequences, I mean Cauchy sequences, right? And it's just the p-adic absolute value of their difference, which of course is some sort of limit. And yeah, and then it's just the metric topology. You just have a metric space, so it's just the metric topology. Zafar, but that is an interesting question. I will come to it in a second. Hopefully, maybe. I need to keep it short. I'm worried about my thesis. But I want to try and say what the Adeles are. Not sure why, but YouTube doesn't like your comment on the proof of 120. Oh, weird. It's just the perfect number for things not to be quick. And for some mysterious reason you find it satisfying. Well, maybe we'll do that. Maybe I should have a to-do list here. To do. No simps 120. And what's the other one? A matrix of the form I plus epsilon b have root near 1 0 0 minus 1. Okay, yeah. What's p-adic then? That's a thing? Yes, p-adic is p, but sometimes you need to use a different prime because you already have a prime p floating around somewhere. Hang on, we're not done the Adeles yet. The co-limit of the direct sum of co-sheaves, tensor multiplied with some weight function, and the characteristic function of some mapping on a projected space. What? Okay. Well, I don't understand any of that. But let us know when it's out, and we'll take a look, and then maybe I'll understand it. I mean, I understand all of those words by themselves. Okay, anyways, so we have all of these fields, and we can do integrals on all of these fields. Yay! But there's infinitely many fields. No one has time to sit down and do calculus on all of these fields separately. So we decide to multiply all of the fields together and get this big giant topological ring. Oh, the Fourier-Mukai transform. Wait, is that the Fourier transform that on? No. Yeah, is that the perverse sheaf Fourier, the Fourier transform on the derived category? 120 Simps was one of your written qual problems. Nice. I've been thinking I should be putting out shorts where I just solve a bunch of qual problems. I think that'd be fun. Okay, so what am I doing? Right. So we want to how can we take the direct product instead of the direct sum? That's an interesting question, actually. Uh, that's an interesting question. Hmm. Yeah, it applies to perverse. Yeah, I think you can define it generally on the derived category. Actually, that's an interesting question, Ken. I've never really thought about that. Um, I have some ideas. There's a theorem I could say that makes things sort of interesting from a multiplicative standpoint. Um, I mean, if you take, because for instance, if you take a rational number, and you take the product over all of these, then this is one. Um, so I don't know. Vibes wise, there's something nice going on with multiplying everything together. I guess I would say that. Um, Yeah, in a direct sum, you can only have finitely many non-zero quantities, but oftentimes we want that, right? Uh, like that's true, but why wouldn't I want that? That seems nicer and more controllable. Uh, yeah, I think I think I think you could maybe say something about this and the behavior of integrals. I mean, as a post hoc, I can tell you some nice theorems about analysis on the Adeles, and then as a post hoc rationalization, we could say, well, this was the right thing all along. But why did people do this in the first place? I don't know. Maybe you should investigate the direct sum. Okay, but the problem is, there's a problem with this. The problem is, if you do this, now this whole big ring fails to be locally compact. Oh no, we're so sad. This big ring fails to be locally compact. So, what then? Well, we fix this because each of the p-adics has this crazy thing called the p-adic integer sitting inside it. Um, it's a compact open ball, but also a subring, which is incredible. And so we fix the failure to be locally compact by making the following definition. Let me just move this bad boy down here a little bit. Yeah, go down there. Okay. And ignore the double negation. So then what we do is we take what's called the restricted direct product. So we go R times the restricted direct product over the finite primes, where now the condition here means that for every element, so we could write it x2, x3, x5, dot, 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 for every element belonging to here, all but finitely many, so what we might say describe as almost all but finitely many xp lie in zp. So if you do that, that's the fix. And so now this thing is locally compact. And so the Adeles of the rational numbers are exactly this thing. And now, what's really cool about this, so we can still do, for lack of a better word, calculus. We can still do Fourier theory on the Adeles, except now, and it's also, so now we're simultaneously doing Fourier theory on all of these fields, and there's this like compatibility where you can like, you know, break up integrals over the entire Adeles into some product over all the individual integrals, and there's a sort of back and forth between the local and global theory, which is just, you know, a big theme in geometry, number theory. Yeah, all of math, really. It didn't send the message with double like weird. Why is there so many messages not being sent today? Yeah, yeah. It wouldn't have the original field embedded in it, um, which you could count as a negative. But then also like why? You know, so last night someone asked me why do we care about the Fourier transform? And in some sense, I mean, this is Leo. Are you here? This is me. This is me being stuck by language games again. Still, but I was like, why do we care about the Fourier transform? Like, it's everywhere in my life. You know, it's everywhere in my life. Oh yes, exactly. That's a good point, Ken. Yes, we would want the all one sequence to be a multiplicative identity and get a ring. Yeah, so there's a good thing, but. Mm, so let me just say one last thing on this. By the way, you can play this whole game for any number field. So take a finite extension f over q, and how are the Adeles defined? Well, for you take first your first factor now becomes product over all the Archimedean places. So that's all embeddings, uh, all embeddings of your number field into complex numbers. Well, you only take one of each of the real embeddings, but the all the complex embeddings come in complex conjugate pairs, and you just pick one of those. And then what's the other product? Well, you take the ring of integers. You take the ring of integers, and you take the product over all prime ideals, and you take the math frac p-adic completion of your field there, and you're laughing and having fun and a really good time. So, yeah. Good question, Russ. Well, there's a couple other questions. There's some other questions here first, and I feel like I should actually go right away. Um, uh, but how about this? I would encourage you to consider an example. So look at the group Z mod 6 direct sum Z mod 10. Look at this group, or maybe an easier example just to make it smaller. Look at the group Z mod 6 Z mod 4. So I want you to look at this group and to compute a bunch of different. So actually sit down, write out something like 1 2, or 1 1 even, and actually go through and compute. Okay, 1 plus 1, that's 2 plus 2, that's 3 plus 3, or sorry, 3 3, and you add 1 1 to it again, and this becomes 4 0, and you add 1 to it again. So go through and do that with a whole bunch of elements, and I think this will be better than anything I could tell you, is for you to actually get your hands dirty with an example and internalize it. You're here, but mostly learning Pink Pony Club. Learning it? On what instrument? So many problems are just much easier in wave space. I guess so. Yeah, I mean, the one explanation I gave, because I was like, oh, Fourier transform, that's like all over everything that I do. But then I was like, how do I how do I succinctly say why we care? But the answer I gave was, well, sometimes if you transform a problem like a differential equation, it's easy. You could solve it in the transformed version and then transform back, and it's easier. Geometrically, an Adele is like a stalk of a rational function at every point. I suppose, yeah, a stalk at every prime. And rational functions typically don't have finite support. HSP, I don't know what that is, which breaks most public key cryptography when you can do quantum Fourier transform. Raymond, I don't know why your messages are getting blocked. That's weird. It is probably Leo's fault. Yeah, absolutely. Yeah. Anywho, I think that will do it for today. So sorry about this unsolved question, but yeah, maybe I will see this tomorrow and we'll remember. We will maybe talk about matrices having a root near some other matrix, and yeah, I don't remember anything about matrix roots, so that will probably involve me looking things up, and then proving that groups of 120 are not simps. Easy peasy lemon human life. That is exactly how the saying goes. I would know because I invented it. Hello, Farzan Imran. Yeah, I'm leaving. I am serious about leaving after 20 minutes because this thesis, I was just about to say it. Holy shit. Yeah, the thesis ain't gonna write itself, as Arad said. So, yeah. QED, QED, QED.